Welcome to Lecture 20, entitled Surface Integrals. In this case, we're going to be looking at scalar functions and the computation of flux using the explicit representation. And again, this material is coming from Reading Assignment 4, Section 1.6. The objective in this case is to compute the integral of a scalar density over a curved surface and a flux in 3D using an explicit representation. The concepts and visualization skills associated with this lecture include mapping from a planar surface in the XY plane to a curved surface. In the last lecture, we were going to a UV plane. Now we're actually dealing directly with the XY plane. The Riemann sum in this case, the construction of a differential surface area vector, and computing the magnitude of the differential surface area vector. As usual, the second slide is just an outline of the presentation to follow, so we will just skip over it. All right, so here's an example of explicit representation of the surface. We're generally using the same surface as we did for the case of parameterization of a surface. And the objective is to map points on a planar surface region R in the XY plane to points on a curved surface region S. And in this case, it's defined by Z equals square root of x squared plus y squared, which is more or less the equation of a cone in 3D. So in this case, the position vector is going to be functions of only x and y. And so it's actually somewhat easy here because if the function of the surface is given to you explicitly, then the actual components of the position vector are x, y, and z, where z by definition is a function of x and y. So in this case, if you graph out the function, you end up with a cone. And the region basically in this case is going to be from minus 4 less than equal to x less than equal to 4, and root negative 16 minus x squared less than equal to y less than square root 16 minus x squared. So we're interested in basically just looking at the exterior surface area that takes you up to z equals 4. And if that's the case, then what we're seeing is a region in the xy plane, which is a circle of radius 4. Now what's really interesting here is that intuitively, it's much easier to understand what we're trying to do when we're doing an explicit representation. What you see here is more or less a projection of this surface onto the XY plane. So the shadow cast by this object is this. Now imagine you have a differential area in this region, and that maps to a differential area here. And so the thing that will happen is that you'll have a differential area here, which will be some multiple of the differential area here, depending on the nature of the curvature of this surface. So in this case, since every point basically is linearly related to any movement along here, no matter which direction you're going, we would expect that we would see a scalar multiple, like the differential area here and the differential area here will be related to each other through some scalar multiple. And you'll see that that will be the case, but that's something you can sort of immediately see when we're dealing with an explicit representation. So this is something to make note of because it's somewhat easier to understand the notion of integration, double integrals, when we're dealing with curved surface in an explicit sense. Okay, so given that we have set things up, then we want the explicit representation of a Riemann sum. So scalar function and flux we were interested in, as we were with the case of the parameterized representation. So in this case, we're parameterizing with respect to the variables x and y. So the charge density at any given point on the surface is related to x, y, and z, which is the actual point on the surface. Evaluate x and y. This is the explicit representation of the function of the surface. In the limit, basically as you make the surface area elements smaller, and you need more of them to fill out the space, this in the limit becomes the double integral of sigma x, y, z, where z is valued at xy ds. Delta sk in this case will be txk cross tyk magnitude, delta x, delta y. And the differential charge associated with a specific surface area element now will be xk, yk, z evaluated at xyk, delta sk. So this is a differential charge. And again, the units of sigma are coulombs per meter squared, which is the charge density. In the limit, delta becomes d. So this ds is the magnitude of t subscript x cross t subscript y dx dy. In the case of flux, we're taking the dot product between the vector field at a given location times the differential area at that location, and you're summing over all differential surface patches. And in the limit, you end up with the total flux and this double integral. So f of k basically would just be the coordinates of the vector field, but now the coordinates are with respect to x, y, and z, where z is a function of x and y. So this is the x coordinate, the y coordinate, and the z coordinate for the vector field f. In the limit, then, this is just a continuous function. It's not looking at individual differential areas basically indexed by the subscript k. Here it's just a continuous function. And this is the flux density. So delta sk in this case would be t delta xk cross ty subscript k delta x delta y. It's a differential area vector. And this is the differential flux associated with the differential area. The units of f of k will be some symbol, number, flux divided by meter squared. So in this particular example, the property could be the current in amps, for example, in which case this really ought to read current flux. Okay, they normally would say current, but in actual fact, we would say current flux. That way you know that we're dealing with a vector field rather than a scalar. Okay, so the word flux tells you vector. All right, in the limit, the delta s at k becomes ds, and it will be just tx cross ty dx dy. Okay, so let's take this example and that we just dealt with earlier and just work it out for a given situation. We're talking here about a thin sheet described by the surface z equals square root of x squared plus y squared. For z, 0 less than equal to z is less than equal to 4. And the density of the sheet in grams per centimeter squared, this is CGS units, is rho equals fxyz equals 8 minus z. Compute the mass of the cone. So this is a surface density of mass on this cone, and we want to know what the total mass of this cone is. So again, step 1 is parameterization of the surface, and that's just going to be position x, y, and z is a function of x and y. We know what the z value is. It's just square root of x squared plus y squared. So here's our position vector. And the region over which this occurs will be from minus 4 to less than equal to x is less than equal to 4. And for y, it's between minus square root of 16 minus x squared and root 16 minus x squared positive. And so this defines this purple region. This is purple region is nothing more than the projection of this surface area onto the xy plane. So step 1 completed. So now let's move to step 2, and that is to compute the magnitude of the differential surface area, which from previous expression is the magnitude of tx cross ty times dx dy. And just to recall, the position vector r is just x, y, z, where z was described as a surface of cone, which is square root of x squared plus y squared. Next step is to take the partial derivative of position vector with respect to x and the partial derivative position vector with respect to y. And so in the one case you get this vector, and the other case you get this vector. Next step is to take the cross product between tx and ty. And if you follow through just using the determinant formulation, you end up with this expression. And then making a substitution for dz partial x and dz partial y multiplied through in both cases by minus 1, we end up with an expression that looks like this. Now this expression basically would indicate a surface area vector which is pointing inwards from the cone, which means pointing in this direction on this side and this direction on that side. So next thing then is to sort of put things together. The magnitude of the differential surface area is just the magnitude of tx cross ty dx dy. You could also write as an iterated integral, and we will see that in fact it's preferable. In fact, the only way to do the integration is to dy followed by dx. And so if you plug in then the expression for the magnitude tx cross ty, then this would be the magnitude, and if you put in dz dx and dzy expressions, you'll find out this just becomes a scalar constant, square root of 2, dy dx. Now earlier we mentioned that for a cone, if you basically look at the projection of the cone onto the region below in the xy plane, a differential area that maps from the xy plane to the surface doesn't seem to change depending on where you are in the region. And so we anticipated that the relationship between a differential surface area patch on the surface versus its corresponding point in the region below would just be a scalar factor. And in fact, that's been confirmed because we find it's just a factor of root 2. So the last step basically is to compute the total mass, which is to integrate rho ds over the surface of the cone. And so here is rho now, function of x, y, and z, but z is the surface of the cone, and this represents ds that you see here. So if you put in the rho, which was 8 minus z, but z by definition, because it's the surface of the cone, is the square root of x plus y squared, and then root 2 dy dx. Notice here, the inner integral is y because the bounds on x, but the inner bounds are with respect to x. So this is one semicircle, that's another semicircle. Now this integral is a bit more complicated to integrate, and so the simplest thing to do is to convert this into polar coordinates. If you convert to polar coordinates, then dy dx becomes r d theta. And since this represents a circle of radius 4, then in polar coordinates that means a radius from 0 to 4, and going once around the circle is an angle from 0 to 2 pi. And finally we end up with a result of 379. All right, so the last example is rain flux on a slanted roof. So in this case, the problem statement is to compute the flux of rain hitting the slanted roof. The flux density is F equals 0, 0, minus 1, which means it's downwards. And direction across the surface, which is the plane is Z equals 4 minus 2x minus y in the first octave. All right, so this is the equation of the plane. And so the region that we'll be interested in is a projection of this section of the plane, which in the first octant, onto the xy plane. And that projection leads to this gray triangle that you see on the xy plane. So the parameterization of the surface is relatively simple. We have xy, and the z component is more or less the equation of the plane. We're only interested in the first octant. So we're interested in x from 0 to 2. 2 would be this point here. And y, limits on y would be y equals 0, which would be this line. And this line here, which is just the equation y equals 4 minus 2x. So the bounds basically for the double integral now are set between 0 and 2 for x and between 0 and 4 minus 2x for y. The other thing we have to keep note of is the fact that the flux is downwards. So if we want a positive value, we want to choose a surface area vector which is also pointing downwards. So when we take the dot product between the two vectors, we get a positive quantity. So the problem statement, in effect, tells you in what direction the surface area should be pointing. Okay, so complete the rain flux on slant roof. The next step is basically to compute ds, the vector. This is the differential area. It's dx cross ty dx dy. We've already have r, the previous slide. It's this expression. Now we take the derivative of this with respect to x, and we end up with this expression. Derivative with respect to y, we end up with this expression. Next step is to take the cross product. Again, this means that you set up the matrix and take its determinant, and you'll end up with this expression here. If you then take the derivative of z, which is this with respect to x, you basically will get a minus 2, but you have a negative here, so this becomes a positive 2. dz with respect to y would be minus 1, but you have a minus 1 here, so this becomes positive 1, and you have 2, 1, 1. All right. But this is a direction z is 1, would be upward. We don't want upward, we want downward, which means we have to multiply this through by negative 1 to essentially rotate it by 180 degrees. So the correct direction for the surface area vector is minus 2 minus 1 dx dy. So the last step is now to compute the integral f dot ns ds. This basically is equivalent to just ds. All right, so we're given basically the vector field, which was 0, 0, minus 1. We now have the surface area vector differential, surface area pointing downwards. We've chosen the iteration integral to be dy followed by dx. Why? Because the region is structured in such a way that the limits on y are between 0 and 4 minus 2x. So that means y has to be a function of x, so it has to come first. And then the last bounds, the outer bounds, are for x between 0 and 2. So if you perform the dot product, then you get a 0 contribution for the first term, 0 for the second, and the last one will give you 1. So that means dy dx, that's why you end up with this. And the rest is just a matter of taking the integration and taking it to its conclusion, and the result is the flux being 4. All right, so this would be a mass flux. Okay, so mass flux would be in terms of kilograms per second per meter squared. Okay, that's the amount of rain that's hitting that would be the flux density in terms of amount of rain that's hitting the surface, and we would be computing it over the full surface area. So we'd be talking about kilograms per second of rain that has to be basically removed by the gutter system. All right, so we have now just a quick couple of pictures sort of summarizing various possible surfaces that you might encounter. And I'm going to give you a slide which has the explicit description and also a parametric description of the same 4 different types of surfaces. I'm not going to go through this, it's in the notes, but it's something here that's quite useful. So for instance, what you have here on this column are the equations describing the surface. If we're using an explicit description and you're dealing with surfaces which form closed contours, you need to basically describe in terms of 2 different surfaces. So for example, here you have the right half represented by this. This involves a square root, and the left half basically needs a minus square root. All right, there's no way basically of describing this using a single function when we're dealing with an explicit representation of the surface. Anytime you have a square root, you know you're going to have basically deal with 2 parts. So here's another example: the upper hemisphere and the lower hemisphere. So if you have all the information, then you can basically compute tx cross ty, and so that's what I've done. This is the expressions that we need to develop, and then these are the specific examples, you know, for this case, for this case, for this case, and for this case. Okay, for parametric description, it means x, y, and z as described in terms of variables u and v, and in this case, you can see here, for instance, with u and v, we can represent a closed contour with just a simple parameterization with limits on v and u. So these are the same 4 examples as in the previous slide, but using parametric description of the surface rather than explicit description of the surface. And so if you follow through, you'll end up clearly with different expressions, but when you do the integrals, you'll end up exactly with the same answer. Okay, so just some general guidance here, summary in terms of computing surface area integrals. The question that arises, how do you determine if a parametric or explicit description of a surface is the best choice? So these are sort of general guidelines. So first is, if the surface is given explicitly as z equals a function of x or y, then generally the explicit approach is the best choice. Second, if the surface is bounded by a closed smooth contour, then the parametric approach is the best choice because you essentially don't have to break things up into, you know, an upper and a lower bound. You basically can parameterize the whole system just in a single go. If it turns out if option 1 or 2 apply, if neither of the options 1 or 2 apply, then the reader must experiment to see which of the 2 approaches is easier. Generally, the problem is stated in such a way as to explicitly state the choice to be made, or by inspection it is obvious which approach to choose. Okay, and so the last slide now is just trying to group together all the equations that we have basically described over the period of this lecture and the previous lecture, sort of in one common place. And so we have the starting point, which is a position vector, the vectors defining the tangent plane, the unit vector that's normal to the tangential plane, ds being the magnitude of the differential area, and ds being the differential area vector, which is the unit vector times the magnitude of the differential area, which is the same here. And so we had the parameterized representation, and so I basically just sort of summarized them here. And we had the explicit representation, and I basically summarized them here. What I haven't mentioned here, that not only do you need the parameterization, but you also need the bounds on u and v in this case, and the bounds on x and y in this case, because those bounds are the ones that you use for the bounds on the double integral. So here I've just sort of looked at the case when you're dealing with integration of a scalar function over surface area. And so here it's written out basically in a parametric form. And here it's written out in an explicit form. And if we're dealing with flux, which is a dot product between the vector of some vector and a differential surface area, then this is the way I would write it if I'm dealing with a parameterized representation of the surface. And this is the way I would write it if I'm dealing with the explicit representation of the surface. And again, just to remember here, there are two options for the surface area, pointing upwards or downwards. The problem statement or convention will dictate which version to adopt. Right? So that more or less concludes Lecture 20. Thank you for listening.